Hi there. The purpose of this video is to give students who were absent while we were taking the notes in class an opportunity to get them down, or maybe I was going too fast, or maybe we just didn't finish the lecture. In any event, that is the purpose for this video. Do remember just a couple things. Please number all of the items for the notes, and also all class notes need to be in Cornell note style, questions or prompts on the left and answers on the right. I will not be taking as long to move through these slides as I do in class, but because this is a video, you can pause it at any time. Also, I really encourage you to, when we get to the check for understanding slides, to use that as an opportunity to look back at your notes and to try to consider what the answers are. Every couple minutes you spend doing that is a couple minutes you won't have to spend studying for the tests. Yeah, without further ado, here we go. Chapter 2. Scientists do. Oh, also, if you are muting the video, I'm not going to take it personally. Matter of fact, I'm not even going to know. But in any event, while we are scrolling through these slides, I'll be on my phone looking up other tidbits. But totally get it if you want to turn the volume down and listen to your own stuff, or just simply have some silence. What do scientists do? Their job is to figure out how nature works, basically. And if you've never seen the Muppets, you should check them out. Classic stuff that I was raised on, and never remember the scientist's name, but the guy with the orange hair, famously named Beaker, gets himself into all sorts of trouble. So we use observation, we measure stuff, use experiments to determine whether or not our hypotheses are correct or not. I'm moving ahead in about 5 seconds, so obviously if you're still writing, now would be a good time to pause the video. I will always warn you when I'm about ready to move ahead to the next slide. Scientific method steps. There are a bunch of different versions of the scientific method, but they all start with a problem or a question, typically to make sure that your experiment is going to be a solid one. You're going to want to research the problem or the question a little bit before you set up the experiment. This book does not include designing the experiment, but obviously that's an important step. Performing the experiment, during which we will be collecting data. Take a look at the data. If the data supports your hypothesis, then you can publish your findings. If the data does not, typically what is done is you redo the experiment at least a couple times to make sure you didn't make any mistakes. And if it still comes out where your data is not supporting your hypothesis, then you would modify the experiment and redo it. You, of course, do not change your hypothesis to fit the data. That would be cheating. Theory. Basically, a theory is the next level of certainty above a hypothesis. It's basically a hypothesis with a lot of evidence. For example, evolution is just a theory. Even though many, many people believe in it, still many, many people do not. Probably will never become a principle or a law, simply because there are cultural beliefs that are contradictory to that idea. And we advance with our understanding of science. Many times scientific findings lead to new experiments and new ideas. Scientists peer review each other's work to make sure that no mistakes are made, and that is a good thing because it eliminates pseudoscience, science that actually isn't science, and it holds scientists to a higher standard, which is always a good thing. All right, moving ahead to the next slide in about 5 seconds. All right, here we go. Critical thinking is really, really important, especially if you get a lot of your information from the news. some of what you see on the news, and it doesn't matter what news station, is absolutely true, especially, in my opinion, cable news. Cable news, there's a lot of opinion in that as well. So if you find some information on the internet that is important to you, on television or on it could be the internet, news in general, you should search out the professionals who are responsible for verifying that information. So a law in nature, well tested, widely accepted. It's kind of odd. This book does not include the step of certainty of a principle, like the principle of segregation for genetics. But a law is the strongest or the most certain of all of those steps of certainty. Getting ready to bump ahead to the next slide in about 5 seconds. All right, here we go. So reliable science means that most, if not all, experts agree with the idea. Unreliable either means no professionals have reviewed it, or it has been discredited as being wrong. Tentative science could be totally legitimate science, but maybe it just has not been reviewed enough by other professionals. It's a process. Limitations. So scientific can't actually be proven with 100% certainty, nor disproven with 100% certainty. Best you can do is come up with a high probability and hope that that high probability is good enough for people to subscribe to that idea. All right, moving ahead in about 10 seconds. All right, here we go. Again, please use this as an opportunity to practice a little bit with your notes, see how much you've actually picked up along the way. All right, so first number would be the lowest amount of certainty, and then the highest number would be the highest level of certainty. And you would need to look back at number 2, 2 and 3, 2 and 3 and 7. All right, so if you remember from other science classes you've taken, hypotheses come from observations. So an observation would be the least certain. A hypothesis would be next. A hypothesis with a lot of evidence can become a theory. And then, of course, if more evidence is added and most, if not all, professionals agree with it, then it can become a natural law. I take a look at number 9 for this one. Yeah, so can't completely or conclusively prove or disprove science. I'm sure there are probably a few exceptions, but in general, and then the best we can do is just come up with a really, really high probability, and hopefully that's good enough for folks. All right, moving ahead. All right, so definition of a system. Okay. It's really difficult to predict what's going to happen in nature because there are so many variables in natural systems. Some examples. Other examples that are in the book are television set, the planet. Obviously, the planet is a really large system. You have inputs, you have a flow within the system, and then you have an output of matter, energy. You could abbreviate capital E for energy. And just a reminder, I do remind you guys in class about this too, is you don't have to write down everything word for word. You can paraphrase, you can abbreviate, come up with acronyms. It doesn't have to be word for word, but I do want all 22 or 23 items, okay? And I don't want you to be lazy. If there are 9 bullets for you to write down and you write down 2, that's just not putting in the effort that I'm looking for. Feedback can affect their behavior. Briefly started talking about feedback loops yesterday. Getting ready to bump ahead to the next slide. All right, so just draw that. Whenever there's a diagram or a picture that I want you to draw in the notes and you can't fit it all on the right side of your page, please use the entire page from left to right. If that's still not enough room, you might consider, going just to the next page and turning your paper sideways so it's landscape. Do what you need to do. I'm totally okay with this not being on the right side of the page, though. And it says in the book here that outputs into the environment, outputs are going to be matter. So that would be like waste and pollution. Energy, obviously, would be the heat example. Information, actually, work or products too. So products could be matter. Work could actually be energy as well. Also, it mentions that economic systems, there are some examples back on page 20 in your book in chapter 1. Also on page 21 in figure 113, 114, and 115, if you want to go back and check that out. Okay, feedback. So we talked about feedback loops the other day and how a lot of students have a misconception that a positive feedback means that it's a good situation for the environment and a negative feedback is a bad situation. The word positive and negative have nothing to do with that. Positive feedback simply means that the output of the system causes it to happen again. So the output, it turns into an input for the same system. Perfect example of that that was in the warm-up question is climate change is melting the permafrost, which is releasing CH4 or methane to the atmosphere. So methane is the output. Methane's a really powerful greenhouse gas, which heats up the atmosphere more, which heats up the surface more, which melts more permafrost, which releases more methane. So that's kind of a cascading effect, or it exacerbates the problem. That's an example of positive feedback. Negative feedback, like for example, more clouds because of a hotter temperatures or evaporating more water. Clouds actually reflect sunlight, which means that less sunlight actually gets to the ground, less sunlight um, 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 adds heat to the atmosphere. So that counteracts the heating. And it brings it back closer to an equilibrium. That would be an example of negative feedback. Okay, so it has nothing to do with whether or not it's good or bad for the planet or the environment. It's just whether or not the output makes the system happen again and again and again, or if it brings the system back closer to an equilibrium and counteracts that effect. Okay, so we're going to abbreviate FL for feedback loop. So system changes more in the same direction, or it gets worse. And it's not necessarily a negative thing. There are examples of positive feedback that are not bad for the planet. Negative, which is also referred to as a corrective. So changes is an opposite direction, or it counteracts. Also says here that, let me see, I don't think we're actually going to cover this in the notes. It says that when a natural system becomes locked into a positive feedback loop, it can reach an ecological tipping point, which is a vocabulary word in chapter 2. Beyond this point, the system can change so drastically that it suffers from severe degradation or collapse. So, I mean, the book is putting a spin on, positive feedback loops and tipping points as being a negative, but not all positive feedback loops lead to negative consequences, I guess is what I'm trying to convey to you. All right, bumping ahead in about 5 seconds. Oh, back up. Perfect example of a negative feedback loop is a thermostat. So when it gets too hot, the thermostat kicks on the AC, and the AC brings it back to normal. And the thermostat turns off, and then it starts getting warmer again, and then it starts getting colder again. So it's a corrective or a counter effect. All right, now moving ahead. So this is not in the book, but after teaching AP Environmental Science for 3 years and seeing the mistakes happen over and over again, I thought it would be good to formally include it in the lecture. I have an example in the book of a positive feedback loop. Decreasing vegetation in a valley causes increase of erosion and nutrient losses that in turn cause more vegetation to die, which results in more erosion and nutrient losses. And of course, the perfect example is permafrost melting, releasing methane as well. And what you see there on the left in the image, those are actual pockets of methane trapped in the ice. And what you see there on the right is them lighting one of those methane pockets on fire, just to prove that those bubbles are actually methane, or at least, flammable, I guess. By the way, totally would abbreviate greenhouse gas as GHG. All right, bumping ahead in about 5 seconds. All right, here we go. So negative feedback loops, again, they bring things back closer to an equilibrium, which allows for stability. Positive feedback loops with respect to the environment and climate change typically are bringing instability into the environment and into ecosystems. They have a good example of a negative feedback loop also in the book. Negative feedback loop is an application of the chemical cycling. So, chemical cycling or nutrient cycling. So, carbon cycle, phosphorus cycle, nitrogen cycle, sulfur cycle to a lesser degree. When there's too much carbon dioxide in the atmosphere, the ocean absorbs more. Now, granted, that's getting harder and harder and harder because the ocean's warming up and it's harder to dissolve carbon dioxide in warmer water. But that's one way that the carbon cycle helps moderate the amount of carbon dioxide in the atmosphere. Excuse me. All right, so the rest of this lecture is really related to the, and I typically do these at the end of the chapter, related to the science focus sections that are in the chapter. And I'm bumping ahead to the next slide in 5, 4, 3, 2, 1. All right, so the science focus on page 39 deals with Easter Island. So there was a lot of environmental degradation on that island, and it led to the collapse of that civilization. A small island in the South Pacific was a civilization of Polynesians. And this situation has been studied for years by many different scientists. So they drilled cores. I'm reading out of the text while you guys are taking notes there. They drilled cores of sediment from lake beds and studied grains of pollen from palm trees and other plants in sediment layers to reconstruct the history of plant life on the island. And based on the data, they hypothesized that the population grew. Polynesians began living unsustainably by using the island's palm forest trees faster than they could be renewed. And once they started cutting down the trees and using more of the plants, there was less fuel wood, more erosion because the plants hold the soil together, and then agricultural collapse because the topsoil eroded away. The definition of erosion, by the way, is movement of sediment from one location to another location. So why didn't the palm trees regrow? Apparently there was an explosion of rats that came with them, and the rats were eating the palm seeds. Says, by studying charcoal remains in the island's layers of soil, scientists hypothesized that when the forests were depleted, there were no firewood for cooking or keeping warm, no wood for building large canoes used to catch fish, shellfish, and other forms of seafood. They also hypothesized that with the forest cover gone, soils eroded, crop yields plummeted, famine struck, population dwindled, violence broke out, and civilization collapsed. And there are many scientists that think on a much larger scale in different locations on the planet that might be what happens in our future between now and the end of the century if we lose agricultural land, and if people are starving and people are having to move away from the coastlines because sea levels are rising, that it's going to cause conflict. So the new evidence suggests that the collapse was not a result of starvation and war. They believe it was likely disease spread by some European visitors. And many of you know this already, but isolated populations of humans that have not been exposed to outsiders, they typically don't develop immunity. That's why when you travel to remote, well, not just remote, but other countries, you have to get immunized for the types of diseases they have there. Because Americans, if you've lived here your entire life, your immune system might not have immunity to those diseases. All right, getting ready to bump ahead. Okay, we did a little bit of practice on this the yesterday in class. I am totally okay with you rather than typing this all out. If you're writing it by hand, you should be able to fit it. Again, you can go all the way left to right on your paper, or you can take a picture of these slides and then import them into your typed document if you want. I'm totally okay with that. You don't necessarily have to write it down. I do pause the videos here so you actually can have an opportunity to try the problem. Okay. So 1 ton, you're going to need to know that equals 2,000 pounds. British thermal unit, or a BTU, 12,500 BTUs per pound of coal. 1 kilowatt hour, which is abbreviated as kWh, is 3412 BTU. So that's the given. All right, so how much power in kilowatts per hour can be produced from burning 1 ton of coal? And you're going to need to use dimensional analysis on this. I'll give you a clue. You start with the 1 ton of coal, just like you did on C for the handout that I gave you guys on Friday. And obviously, if you're not watching this video in 2021, I'm referring to the lesson that we did in 2021. Because I plan on using these videos for a long time. All right, and obviously, if you're trying to work this problem out, you're going to want to pause the video, work it out, and then you can see whether or not you got the answer correct or not. And I'm going to show you guys the setup in 5, 4, 3, 2, and 1. All right, so you got to use the pound and ton conversion factor to get rid of tons of coal. And then you have to use the 12,500 BTUs for 1 pound of coal to get rid of the pounds. And then, of course, to get to what you want, your kilowatt hours, you have to use that conversion factor of 3412 BTUs per kilowatt hour. All the units cancel out, and you are left with kilowatt hours, 7327. And if you got that right, give yourself a nice pat on the back. All right. Okay, let's practice with the notes just a little bit. We are finished with them, though. What is a system, and what are tools we use to make predictions about them? So you might want to take a look back at number 10, 10, 11, 12, 13, 14, all deal with systems. Actually, 10 and 11. 10 and 11 for the most part. All right, yeah, so a system is a set of components that interact in a regular way or an expected way. The tools we use, math models, statistical tools. For climatology, we use supercomputers because there's so many variables involved. Yeah. Match them up. Hold on, is there more than that? All right, so match up positive versus a negative feedback loop. So you're going to want to take a look back at number 19, 18, oh, pardon me, 16 and 17, 16, 17, and 18. All right. So yeah, negative feedback loop counteracts the phenomenon. Positive feedback loop, the phenomenon continues and it gets worse and worse and worse. How does methane contribute to global warming? You may or may not know what greenhouse gases actually do. And I don't think we really, hold on, yeah, we did. We talked about that. Yeah, so this is number 19. Yeah, so in number 19, it says methane gets released, a powerful greenhouse gas, warms the atmosphere more. So basically what's happening, and we'll get into this when we start talking about pollution and the greenhouse effect. But so sunlight comes through the atmosphere. Some greenhouse gases can absorb some of that heat energy from sunlight, but the majority of the greenhouse effect happens when land or water absorbs that solar radiation, and then heat radiates up from the surface back into the atmosphere. And a perfect visual example for you of that radiation that you can't see really is if you're walking across like a really large open field, or especially a large parking lot where there are no cars there. The air right above the surface looks kind of fuzzy, looks kind of unfocused, I guess would be a correct way to say that. And that is actually the radiation going back up into the atmosphere. What happens is the wavelength of the incoming sunlight changes from lower wavelength to a higher, longer wavelength after it gets absorbed by the surface. And that longer wavelength is much more easily trapped by greenhouse gases. So basically, the greenhouse gases that are in the atmosphere, and of course we're putting way too many of them into the atmosphere, they grab that radiated energy in long wavelength, and they retain that heat and keep it into the atmosphere. Now, don't get me wrong, the greenhouse effect is necessary for life. I mean, if we didn't have greenhouse gases in our atmosphere to begin with, we'd be like Mars, which is, any water on that planet is frozen. But we are becoming more and more and more like Venus. Venus has an atmosphere with a huge percentage of carbon dioxide. I think 80% of its atmosphere is carbon dioxide. It's a volcanic planet, as Mars once was. And the temperature on Venus, I think, is about 800 degrees. So the more heat you can retain in the atmosphere, the hotter it makes the surface. And of course, that's leading to climate change. All right, ladies and gentlemen, that is it for the notes. Please don't forget to get these submitted on time. This is not one of the assignments I'm going to give you an extra day to upload because you're going to have a couple days to begin with to finish them up and to upload your notes. All right, ladies and gentlemen, we will see you in class.